Continuing with our discussion of Newton's laws, first, second, and third, we are now on to the second of Newton's laws, second of three. And to get started with this law, we want to review a couple key terms that we've looked at over the last few weeks, one of them being force, mass, acceleration, and inertia. And see if you can jot something down, both about what it is, definition, and units, if you know it. So go ahead, pause the video, take a second to fill in what is known about each of those terms. So force we've talked about quite a bit. We know force is the push or pull happening on an object, and we of course measure that in newtons. Force, we looked at both net force, balanced force, unbalanced force. We did our free body examples, right? We talked about how much force of gravity, normal, lots of different examples of force, push or pull on an object. Mass, we've talked a lot about, but I don't think I've given an official definition. Mass is the amount of matter within an object, or how much stuff really an object is made out of. And mass, of course, is going to directly relate to weight of an object, but it's a different measurement. This is actually thinking about how much stuff is there, and we measure that in little k, little g, kilograms, kg. Acceleration, we're looking at a change in one of two variables, either speed, and that speed can of course increase or decrease, and we can also see a change in direction, giving us an acceleration of an object. And that we measure in meters per second squared. Okay, so meters per second squared, not a miles per hour, but meters per second squared, because we're looking, this is the important part, over time. Inertia we've looked at most recently with Newton's first law, thinking about inertia is the property of an object to resist a change in motion. And there's no unit really for inertia. It's a property or a characteristic an object has, so I can't put a unit label on it. As always, we're starting out with our essential questions, thinking about the connection between a couple of those variables we just reviewed. An increase in mass, an increase in force, how are those impacting the acceleration of an object? So really our focus for Newton's second law is thinking about what is the relationship between all of these variables. Force, mass, and acceleration. We're going to be talking about all these variables interchanging and impacting one another. So the second law does a couple things for us. It first tells us that the more force that we apply to an object, the more it's going to accelerate. And the more force you put on the object, the more it accelerates, therefore the more its motion is going to be impacted or changed. Now I like to give a couple examples here. So for one, a grocery cart. Grocery cart is a really easy thing to move around. So if I'm pushing this grocery cart and I add more force to the grocery cart, I'm going to start to see my acceleration increase, right? The more force that I apply to this cart, the more it will accelerate and move through the parking lot. Now because acceleration is either a positive or negative, I can also push harder on the brake of the car, right? Add more force to the car's brake, causing it to stop quicker and therefore accelerating. So both of these examples, the grocery cart and the stopping car, are common examples of when force increases to get the acceleration to also increase. Quick reminder here of our definition. Acceleration is the change in speed or direction over time. Okay, we'll be looking at a couple common force and acceleration examples, talking about baseball, okay, and seeing how force and mass can impact the game of baseball. So do a little brainstorming here about force and acceleration and answer this question in your notes. What's going to be different in terms of force, mass, and acceleration about throwing a ball two different ways? One, horizontally as hard as I can, and tossing it a nice gentle way to my friend over here. Okay, what's going to be different in terms of force, mass, and acceleration, our words of the day? What's going to be different between these two examples? Just take a pause and write down a couple things as you think about it. What's different here about these two scenarios is, of course, force. Right here, the directions where I'm throwing it as hard as I possibly can, whereas here, I'm giving it a gentle toss up into the air. So force is definitely different, and because the force exerted on each ball is different, that means my acceleration will also change. So let's think about how will the acceleration be different as the two forces occur. Well, as we know, when the ball is thrown harder with more force, I'm seeing a greater change in velocity. Okay, velocity directly related to acceleration, meaning I'm having a bigger change over a short period of time. So the more force I apply on the ball, the more I change velocity, which is telling me when force is increased, my acceleration then will increase. And this is kind of big picture here. You might want to highlight, star, circle, underline this idea here, right? When we apply more force to an object, its acceleration will increase. The more I push or pull on something, the faster it will change its speed. Again, another investigation question to think about. If I'm now throwing a softball compared to a baseball, both as hard as I can, why is their speed so different? Okay, take a minute, formulate your answer, jot down a couple things, thinking about our key words, force, mass, acceleration. Why would their speed be different if I'm throwing them the same? We should know here that the difference is due to their mass. Okay, softball is a little bit larger, more massive than a baseball. So if it takes the same amount of time to throw both balls, I'm throwing them both with the same force, the softball is going to have less acceleration, right? Is the larger, more massive of the two balls. Therefore, the force I put on it will cause it to have a slower acceleration than the object with the smaller mass, which is then the baseball. The smaller massed objects need less force to get them to accelerate at the same acceleration as the object with more mass. So again, everything is all connected. The acceleration of the object depends on both mass and force exerted on it. So let's see how we're doing with this idea. We've got a couple practice problems that we want to give a try. Go ahead and check out what we're doing. We've got a change in either mass or force, depending on the object, and based on that change in mass or force, we have to determine is the object's acceleration increasing or decreasing. So go ahead and pause, give these a try. Simply have to write in increase or decrease for each of the answers. So the grocery cart here is going from empty to full. So at the beginning of our shopping trip, we have the empty cart. At the end, we have a full cart. What we've noticed here is that the mass is increasing. And as the mass increases, we should see a decrease in acceleration, right? The more massive an object is, the less likely it is to change its motion, right? Inertia. So therefore, we'll see a decrease in acceleration. Here I've got the same grocery cart, but now I've increased my force, going from 50 newtons to 70. So when my force increases, what I should see is an increase in acceleration. And finally, the delivery truck. I'm going out at 6 a.m., returning at 3 p.m. And because it is a delivery truck, we're thinking about packages inside the box or inside the truck. So I'm starting out with a lot of packages here at 6 a.m. Not very many should be left, if any, at 3 p.m. So my mass has gone down, decrease. Therefore, I should be able to accelerate more in my less massive truck. So officially, Newton's law is telling me that the acceleration that an object has is going to be in the same direction as the net force on the object. And we've talked about this a lot with our free body diagrams already. We've seen that when the net force goes in a certain direction, that is the way that the object will go, because that's where most force is. But if I want to know exactly what that acceleration is, then I can actually calculate using this equation. Go ahead and record the acceleration equation on the right-hand side of your notes. It will be acceleration equals force divided by mass. And I can use that as long as I know the force variable, as long as I know the mass variable. I can plug both in to get acceleration, which again, remember, is meters per second squared. Now I can manipulate that formula a little bit if I need to solve for net force. If I want to know the overall force acting on an object, and I have the other two variables, mass and acceleration, I can do so by taking mass times acceleration. Knowing those two, I can then calculate out the force. The missing variable then, of course, is mass. I can solve for mass by simply taking force over acceleration. So I've got a formula for each one of my three variables that has to do with Newton's second law. Quick unit reminder before we go into calculation: acceleration, meters per second squared; force, newtons; mass, kilograms. Those are definitely units that we need to know and practice with for each equation that we solve for Newton's second law. So our first practice problem here is we want to figure out the acceleration of the Batmobile if we know its mass and we know its force. That always helps me to underline as we go through the word problem to see what I know and what I need to figure out. So I need to solve for acceleration. That's my unknown. So if I look back at my formulas, I should see one formula that is acceleration equals. And that formula is going to be force over mass. Okay, so I need to then solve for both force and mass from my word problem in order for me to calculate what is acceleration. So I have the force here in the word problem as 24,000, really big force. Of course, I want to include my units all the time. My mass then here is 1,200 kilograms. And again, I'm still trying to figure out my acceleration. So now I can just plug those in, right? My force value is 24,000. And my mass value, I can replace it with 1,200 and calculate it out. That tells me the total acceleration of the bat would be 20, and of course including my unit, meters per second squared. Another practice problem here, solving for now the net force for Aaron Rodgers throwing a football, knowing the mass of the football along with its acceleration. So again, net force is my mystery. I've got a mass of 0.4 units kg. I've got an acceleration of 20 meters per second squared. Because I'm solving for net force, I'm going to use this formula, F equals ma, which tells me I multiply those two together. So I've got a mass of 0.4 times an acceleration of 20. That's going to help me solve for Aaron Rodgers' force of 8 newtons. Before the notes are totally complete, make sure you create one of your own word problems on the right-hand side. Come up with some kind of object and fill in 2 of the 3 variables in your word problem, leaving the third one there to be solved for. You do not need to solve it, but you want to write the word problem. You do have 2 summary questions, so make sure you answer those, and you should then have some practice problems to complete for class.